Carl Nomek, with Facility Services, a branch of engineering services. I work with Ken Reestack over in Facility Services. Ken works for Jack Dempsey over there at Facilities. So, retro commissioning. We're a new group on campus. We just were formed in August of 2007. So we're 4 months shy of being 2 years old. The reason why we were formed, or at least as I understand it from Kent, is that there was utility deficits accruing at a rapid rate on campus. The cost of gas was, $4 a gallon. Price of coal was up, so there were major increases in utilities being accrued. We knew that we had a maintenance problem in the buildings. They knew that they'd been underfunded for maintenance in their buildings for long periods of time. Things were deteriorating. Sensors weren't working, dampers weren't working. So the thought appeared to be that, why don't we create this SWAT team, this retro commissioning group, to go out and go through these buildings, try to attempt to save as much energy as possible, try to do as much maintenance, improve the maintenance as far as we could within the resources that we had, and improve the air quality as much as possible. So the title of our presentation, in case you're wondering, is Dana has coined the phrase previously, save the planet one building at a time. Well, we just started a second retro commissioning team the end of January, so now we're saving the planet 2 buildings at a time. There's a lot of things going on in facilities and services in terms of trying to do sustainable things. There's many resources allocated to new projects, like the business instructional facility. It's going to be a LEED project. Lincoln Hall's over there in design. Lots of LEED certification, people being certified in LEED, that kind of thing. In the past couple of years, there's been a lot of chilled water and steam condensate meters being installed in an attempt to get better information on a per building basis across campus. There's our group, retro commissioning. Eva Sweeney has spoken to this group about the lighting retrofits that are going on campus and the improvements that are attempted to be made in that area. And there's steam trap upgrades out there. So lots of time, energy, resources. What is retro commissioning at the University of Illinois? Well, we've got a focused, systematic review of the air conditioning and heating systems. We're really geared to go through the mechanical systems in the building and look those over pretty hard and try to bring those back up to speed to the best of our abilities. We'll incur other things in the building. We'll see plumbing items or electrical things, but the team's built around addressing the mechanical systems. What we want to do is we want to try to save as much energy as possible without overly affecting the operations going on in that building. Think about the buildings on campus. Are those buildings utilized the same way at 2 p.m. in the afternoon as they are at 2 a.m. in the morning? I would think not. Hopefully a lot of those people are going home for the day. Hopefully some people on the engineering campus tend to want to stay in their labs and that type of thing. But we're trying to play on that. We talk about things on a case-by-case basis. In some places, we're able to shut air handling units down. In some cases, we can shut outdoor air dampers at night, shut off exhaust fans, and do significant things in that area. Here's a summary chart. This is through December 2008. We're kind of proud of what we've done here. It's a quick summary of the economic impact of what we've done. Hopefully this is readable in back.
No.
Not at all?
No.
Okay. What we've got here is a listing of the buildings that we've been in to date. There's 11 buildings here. The first building we did was National Soybean Research Lab. We've been in the Krannert Center for Performing Arts, Newmark Civil Engineering Building, Turner Hall, ACES Library, Music Building, the Mechanical Engineering Laboratory, the Animal Sciences Laboratory, the Madigan Lab, and the Chem Life Science Building. I'll focus on this right-hand column to start. We've been monitoring the newly installed metering data, and we've been monitoring the savings of the things once we've incorporated the measures that we've recommended. December of 2008, we just went through past what we believe to be $1 million worth of utility savings in our first, so that's from August of 2007 to December of 2008, so that's a little over a year. So these are some pretty big numbers. We've averaged, in terms of percent energy saved, this includes steam, chilled water, electricity. We're averaging about 27% savings. And we tend to consistently fall between the 25% and 30% range. The Krannert number is a large number up here. It's $400,000. Krannert in FY08 had consumed about $1.2 million worth of utilities. It's an impressive number. We'll talk about how we achieved the energy savings a little later. A lot of the numbers, a lot of the buildings that we get into, our savings rate is in the $150,000 area code. Let's see. We're anticipating to save $1.5 million per year in these buildings. Also noteworthy, just to explain this chart a little bit more, is that we typically initially in a building for about 2 months with our initial team, and then we'll come up with some follow-up projects where we need some controls to be installed or some things to be added to achieve some things. And that's what this column represents. So once we get our controls implemented, then we can truly start monitoring the savings. We will have implemented everything that we wanted at that point in time. So only the first couple of buildings have gone for a full year to achieve those savings. Any questions on this chart? Sure.
Do those savings reflect the difference in temperature and degree days and things of that nature?
We do not typically look at that parameter.
You're just comparing last year's
Meter data
with this year's meter data.
Right. Yes. Any other questions? Yes.
So what about the age of the building? So I see the ACES Library is pretty much brand new.
Good point. That's been an observation of others. We were at Turner Hall. We had 2 pretty difficult, dirty buildings in a row, Newmark Civil Engineering Lab and Turner Hall. They're both 1960s buildings with 1960s stuff. Some revisions have been implemented over the years. Some DVC had been implemented on like the chilled water systems. But we thought we'd stay in the area. We had reason to stay in the area at Turner Hall, so we said, let's go over to ACES Library. Let's give the guys a break. Give them something new to work on. But we found significant problems in ACES Library. There was a pneumatic line off, and all the VAV boxes were open. There were exhaust fans running 24 hours a day, 7 days a week. We could schedule those with the occupancy of the library. You know, the library closes at 5 o'clock in the summertime. So we can do things like shut exhaust fans down and shut some outside air dampers. This number is probably going to way exceed our expectations. We thought we would save about $75,000. This utility data from June '08 to December '08 is showing a savings of $120,000 already.
So it's only half a year.
And that's only half a year. So this number will probably start to get to 200,000, hopefully.
Was it ACES Library Commission when it was built? That was an independent commission, right?
Before my time, I can't answer that. I believe so, but I can't say that with confidence.
Wow.
And how long, do you know how long it had been since it was built that you guys got in there?
ACES Library, 13 years. I want to say like 2000 or something, roughly.
It was in the late 90s, mid to late 90s.
Was that old?
Yeah, so it's been there for quite a while, and I think it's a good point that, you know, it doesn't take that long for things to get out of calibration or not working correctly, and that's one of the reasons, you know, Carl was talking about why they went ahead and did that one, going through a lot of buildings that need controls upgrades. I mean, you got to go in and do installation work. That particular one had some fairly sophisticated controls because it was relatively new. So it was easier to go through it. We didn't have to wait for a follow-up crew. So it worked well. And then we've kind of found that if you can mix some of the different types together, one after the other, you can keep the process moving forward.
Yeah, it's much easier for us to work with buildings at a decent level of DDC controls in it because we can just, rather than installing the DDC controls, we can just manipulate the DDC controls to do what we want and get to our goal typically quicker. Yes?
How many of these buildings have chemical hoods in them, and what impact does that have on the system?
Chemical fume hoods, very expensive. One fume hood, standard width, costs about $5,000 per year to operate. It's 100% outdoor air. We're in a big batch of laboratory buildings right now. Which buildings have had fume hoods previously? Civil engineering has a handful. Turner Hall has many more. There's about 60 plus in there, if my memory is correct. Mechanical engineering lab has a handful. Animal science laboratory has 40, 50. Chem Life Science has 150, 133. Madigan has about 50 also. So we're working tightly. Jeremy Neighbors is in the crowd, and we've been working with the safety guys extensively, trying to work together to achieve some things. Anything else? We'll continue on. One of the big things we try to do is we try to work with people. We try to work with the people in the buildings that we go to. We try to establish a point of contact for like a facilities and services person in the building, somebody that we can chat with about things and bounce ideas off to see if they're acceptable to them or not, and kind of iterate to a solution, if you will. So what this slide is about is, what this slide is about is we have our retro commissioning team, we have our process that we go through, and we have the people that we work with in order to achieve the results. Here is how our retro commissioning teams are composed. We've got two teams right now. Damon is a team leader for one of the groups. We have a DDC programmer. Mike and Ken are with us today. We have a pneumatic temperature controls mechanic, we have a DDC electrician, and we have a sheet metal worker. So we're typically going through all the controls, we're going through the sheet metal, we're doing air balancing work, we're doing traverses, and we find that it works better to have a couple of flex guys to bounce between either team, just depending on workload. And we got about 3 or 4 engineering students working with us. We started out as 5 full-time people. We are now up to 13. So our growth rate has been it's almost tripled since we started. I'm going to hand it over to Damon for a little bit and let him talk about our process.
Well, as it describes, it is a systematic process that we try to apply, a proven method that we've been using for the last 18 months to 2 years. The first step in this process is to gather the data that we can. Next is to analyze the data, and it follows the circle through all the way to the end where we're looking to verify the savings. And we're going to go over each of these steps in depth. Number 1, gathering data. Our goal is to pull as much data as we possibly can about the HVAC systems in the building. So we'll go out and look for any HVAC floor plans, see when it was remodeled, pull those drawings, pull the shop drawings looking for controls to see what's the current sequence of the building. Then we also pull balance reports for a sheet metal technician to review. And then we try whatever we can as well to identify what people in the building know about their building and how they possibly think we can save energy. We next go through and analyze that data. Well, what are we looking for? Well, we're looking for ways that we can save the energy and as well bring better comfort and defer the maintenance or take care of deferred maintenance inside the building. So we create spreadsheets used to catalog all the data of what units are there, how much CFM is it using, what's the air change rate. We build schematic diagrams as well to understand each unit's operation and try to come up with a good general understanding of how the HVAC system works. And we also look at the building as a whole. We found many buildings as a whole are negative in pressure. And so we're trying to perhaps curve that around, change that so that they're more positive involved. We actually send people out to the technicians to verify the field realities. They're out there checking it immediately, checking over the systems. Right now they're at Chem Life in Madigan, checking over the systems. Next process is to implement the solutions. These are all going on simultaneously. So the gentlemen out in the field are out there tweaking and calibrating the temperature sensors, humidity sensors, making sure the system runs through its steps properly. We're inside talking and having meetings, as Carl mentioned, with the facility manager, looking over the occupancy schedules, seeing if we can agree on certain times to cut back the systems, and different other specific solutions that we have in our little cheat sheet. Next step, as Carl mentioned, there's some projects that are too big for us as a 5-man team, so we need to hand those off. Larger projects. To maintenance, for example, at Turner Hall, you're going to see a picture later about this, but there was some definite issues with duct cleaning. It needed to be cleaned, but we only have one guy that can do that. So we contracted and had a separate team from FNS go in and follow us up on that and clean all that ductwork. Engineering support at Krannert Center for Performing Arts. There were some mezzanine units that needed additional controls. Handed that off to engineering support at FNS to design new systems to be installed. Also, we have to solicit capital for bigger projects. The Ively Student Sustainability Committee is assisting us, and we're trying to work with them. The Department of Commerce and Economic Opportunity. And we're funded ourselves out of the AFMFA, or the Academic Facilities Maintenance Fund Assessment. And we try to go back to them as well for the additional funds to move projects forward. Last but not least, we want to verify the savings. We do this by those meter data analysis. There's meters on most of the buildings all that we visit so far to be able to catalog our data. And we use web graphics and utility trending. And I'll show you an example of this. This is the chilled water meter over at Music Building. And as you can see, the tonnage, I'll tell you, the tonnage here is at 140, and then it drops down significantly down to 40 or 50. And what's happening is that people are leaving the building. So as they leave, the cooling load drops off, and then as they come back, the cooling load goes back up. So we're turning the systems off and on every day. And along with this, then, is that we're not needing to reheat. So it's kind of like double the effect. We're not cooling it, but neither are we reheating it. And so we're saving, this drop right here is approximately 70%. cooling each and every night during the summertime and during the off seasons.
So is that a staged chiller then? And you're turning off certain parts of stages at that period? Since
No.
it ramps off and then it drops discreetly?
It's the campus chilled water loop.
Oh, yeah.
So we can just modulate it down. We'll be okay. Then we provide them a building systems manual that they can go through after we leave and consult all the information that we've discovered and hand that off to the people who are in the building so they can continue on with the savings. So the Together We Can, we've discussed the team, discussed the process. Now the extended team we've referenced and many times already, but it has to deal with the people who are assisting us in the building and at FMS. So the facility managers are a big, important part of our process. We meet with them weekly to discuss options in the building, ways we can save energy. Then we also meet with the principal investigators in labs, try to speak with lab monitors as we're surveying and going through the rooms, check on their usage of the rooms. Then we also speak with our route mechanics. A route mechanic is a person on FNS, in FNS, who visits certain buildings and takes care of them from different branches of their trade. So we try to speak with them and get their information. Next part of the team is engineering support, as we commented. Energy conservation, we're working with Terry Ruprecht a lot, and he works with us through the provost office in assisting us. Utilities and accounting, we work with that department to verify our savings. And finally, the communications department assists us with putting together certain presentations or pamphlets and material we distribute. We'd like to show you and do some comments about various buildings we've addressed so far. The first building is a National Soybean Research Lab. We addressed the temperature controls in this building. There was a reference, we were able to shut down 3 hoods, chemical fume hoods, so that's $15,000 a year in that building. Next, we moved on to Krannert Center for the Performing Arts. Carl will address this in detail shortly. Next, we went to Newmark, and we visited there, and there were 37 air handling units that needed improved controls, so repairs. So we worked on all 37 to bring those up to speed. We were able to save 53% in just the chilled water over the time we've been monitoring. Next, we went to Turner Hall. 8 hoods were permanently removed and 7 were abandoned voluntarily. They were trying to work with us as much as they could at that place. Next, we jumped across to ASIS, as we discussed. Just to make note, there was 14,000 CFM running out of the building 24/7. So take that times 5, and that's how much we were able to reduce or 250, so it was only half the time. Then we went to Music Hall. After that, we went to MEL, and then the Animal Science Lab. Currently, we're at Chemical Life Sciences Laboratory. Number 9 there means it's number 9 user out of the top 80 energy users on campus. And then Edward R. Madigan Laboratory is number 10. And next, we'll be going to Loomis Laboratory, Team 1, and Warler's Hall with Team 2. Now we'll turn it over to Carl to specifically address 2 buildings particularly.
Spend a little more time on Krannert. What we found when we got to Krannert is the air handling unit systems were running 24/7 there. You know, we're talking about hundreds of thousands of CFM. You know, the Great Hall was running full speed overnight. There's 3 large venue spaces in the Krannert Center for the Performing Arts, if anybody's familiar with that here. So we were able to go from systems running 24/7 to shutting them off from like 11 p.m. till 7 a.m. in the morning. We were able to run the units half speed during the day. We're doing this all in concert with the facilities guys over there. It was at the time Bob Goss and Randy Grieber and some of those guys. We were able to add CO2 sensors in the Great Hall. So during the day when that venue was empty, you know, we're measuring the CO2 level because that corresponds to people breathing in the space. So it correlates to number of people. If the CO2 level is low, then we won't open the outdoor air dampers to bring fresh air in. We did that in all the 3 venue spaces. We've got a picture of some flood ductwork we'll get back to later. Mike and some of our temperature control people, we were able to put in humidity sensors and temperature sensors to measure the quality of the return air coming back. We wanted to use Mother Nature as much as we could for cooling purposes and bringing in appropriate outdoor air. We don't want the air to get too humid, so we're being careful about that. At Cranard, they had wanted temperature control EDC web graphic web pages for years, and I'm a big proponent of that. So we got together on that and gave them web pages to look at their mechanical systems. They wanted to be able to manipulate things when they had a performer coming into Great Hall, or they're doing recordings. They didn't want to have any air noise. They wanted to be able to control their destiny. So we were able to open up the black box of controls for them and give them some viewability. Direct visual controls.
Whose system was in over there? Whose PDC system?
Let's see. That was an existing Invensys system, but there is kind of a Siemens front end there now.
Yeah.
So. Any questions about Cranard?
Yeah, and how long does it take you to do one of those meetings? For the team, how long? How many days or weeks? Or
2 months.
2 months with the whole team, the five guys working?
Yes. That shows on the earlier slide. Our initial team is in the building for 2 months-ish. And then there was about 2 to 3 months of follow-up controls that were done there. So it took about 6 months in total to go from start to end, I think, roughly. Actually, it never ends because there's other projects that are still coming that will save more energy at Cranard. The music building. We were in here last summer. We were working with an architecture professor, Jim Anderson, who is in the leadership of the administration of this particular college. After talking with him, we were able to shut air handling units off at about 11 o'clock at night until 7 o'clock in the morning. So you think about that, that's about 8 hours. So that's 8 divided by 24, that's about 33% of the time. So that starts to add up pretty quick. And then you got the weekends too. And we're trying to take advantage of Saturdays and Sundays and do some things. We'll get to that in a minute. Again, we were able to shut off some exhaust fans. We implemented web graphics. And they had a new facilities manager starting over there last summer. And this was great for him to get oriented to the building. And one of the smaller festering things we found was a three-way valve on the chilled water systems. Three-way valve means that the chilled water either goes through the coil or it gets bypassed and goes back to the Avid power plant. And we were scratching our heads, going, why do we have 35 tons of load here at the dead of winter and no cooling in the building? When they put the chilled water loop in, they had changed most of the chilled water valves out in the building, but one was missed. So we identified it. This valve was flowing about 200 GPM of chilled water. It was only picking up maybe a degree or two of heat just as it went through the building, but that amounted to 35 tons. So 35 tons running 24/7 will accumulate into a power bill that I don't want to pay.
That you were then heating in the winter also.
Yes. Was there heating? We don't really think so. It was just picking up building heat. So I guess in that respect, and from that perspective, the building was heating it to some degree. Graphics. I want to show you some of the almost real-time graphics and give you some examples of that.
Question, do you guys, on something like that with the chilled water, do you track or do you try to go back to the plant, pick up the savings from, I mean, that kind of degrades the plants, the split at the plant, you know, the delta T, because if you're passing that through, you're eroding that temperature difference, and that's going to have some savings back at the plant. Did you try to calculate any of that in or capture any of that?
No, that's beyond our scope. We're most interested in what's happening on the building.
Within the building.
Yeah.
It does figure into the energy rate because they do monitor the chilled water usage in the building, and that gets applied a rate. It's an average rate for tonnage, but a part of that is the pump horsepower, and that's where you have your energy savings.
Right.
So it is in that rate, but it's more of an average than a specific calculation.
But the dollar values that we saw were strictly based off of electrical meters.
No, that's all three.
Okay.
It includes chilled water, steam, and electricity.
Yes. This is the front end of our Inventus TAC control company that changes its name every couple of years. What do you got? TAC. This is kind of an inventory of where we do have DDC controls on a building. This is a growing thing fairly rapidly. We're going to look at the music building here for just a little bit. What you can see here is there's, what do we got? We got 8 air handling units in the building. 8 air handling units with DDC graphics. AHU3 is missing. It's just got pneumatic controls on it. But let's go to AHU9 for a minute here on the 5th floor. This is a typical graphic. We'll get to the blinking red light in a minute. What we got here, here's the typical arrangement of an air handling unit in a building. We've got a supply air fan, we've got a cooling coil, we've got a humidifier here that we don't think is working. We've got a return air fan, and we got an outdoor air intake, exhaust, return air damper. So we've got all the data here. The blinking red light is a low humidity alarm at the moment. So the guy in the building can see that and write a work order if he deems necessary. Let's see, what else? It looks like the outdoor air temperature is about 50 degrees. We've got a summer-winter temperature set point of 57. We're still in winter mode, so we're taking, what that means is we're taking all the outdoor air from Mother Nature into the building yet. Once it gets to 57, we'll enable this cooling coil and start to provide some cooling. Let's see. Lots of temperatures, lots of data here. I won't go into that. Let's go back.
Can I ask you a question?
Sure.
Why 57 degrees? Doesn't it seem like it's kind of cold for buildings up that fast?
That's a typical number for engineering design. And you could have a room in the building that needs full of people and it needs cooling. So standard discharge air temperature is typically between 55 and 60. So once we go beyond that, you run the risk of heating some rooms up and some people not being satisfied in heavily occupied areas of the building.
And that's heated up later on again if it needs more heat?
Yes, there are reheat coils, hot water reheat coils. So now you're touching on the energy thing. We're discharging 55 degree F air, but your room thermostats are set at what? 70, 72, 74, whatever the room occupant designates. So that's almost 20 degrees of reheat. And that air is just going around all day long like that. So you can see when you start to shut systems down, you can start to rack up some significant dollars pretty quickly.
Are there any areas where you've identified in buildings that you can raise that 57 degrees based on any areas that don't need as much reheat or you could?
That's tough.
Yeah.
Typically in this building, it's pneumatic controls throughout the terminal devices in the building, the reheat coils, the room thermostats. The only place we got DDC is at the air handling Now, our newer buildings will have DDC throughout, but this particular vintage does not.
So there's some buildings on campus where you might be able to look at that as a whole system and
Haven't done that yet.
That's correct. We are doing some of that in some of the newer buildings like
Okay.
business.
You mean like a reset strategy where you
Right.
pull the boxes and say, hey,
Correct.
if they're all in reheat, we can start resetting temperature up to.
Yeah, we can, and typically we either can reset the temperature up, but those are all a little different. You know, most of those are variable air volume, so you're not necessarily reheating all your air either. You cut the airflow back to, you know,
Right, your
minimum
minimum,
rate
your
before
minimum
you
flow
reheat.
at that point in the
Right.
box, yeah.
So, but we do look at resetting on the newer ones where we have the electronic feedback from the rooms.
Yeah, we've commissioned a lot of that strategy and it really works well, and a lot of universities are doing that.
Yeah, we're either reset it on temperature or some strategies are to reset the pressure set point.
Yep.
So,
Here's just a quick chilled water isometric. If you can click on the tonnage trend chart. What we've got here is a chart similar to what Damon had showed earlier. It's got about a week's worth of data here. Apparently we had a warm day back there on April 2nd where we needed a little cooling, but otherwise we haven't needed any cooling at this location since that point in time. So we're trying to bring some of this utility data to the facilities manager and to the building level. We do have a steam heat exchanger in the building. This heats all the water and goes into radiation and reheat coils. This is kind of a complicated graphic for this building. There's 4 hot water pumps shown here. So there's some information about the heating system. I won't belabor that. I think we're running a little short probably. So, and there's the utilities thing here on the bottom. And we just are doing some chilled water and some steam measuring, both cumulative usage and weekly usage trending. Let's continue on. Some things we've encountered. This is the show and tell picture session of the program. It's amazing what we find out there. This was they called it an air silencer at Craner. This is like a 5-foot by 5-foot thing. Whoa. What this is 20 years worth of dirt accumulating on here. Somehow a section of cardboard got in here. Very dirty. We ended up removing this assembly at Craner and just getting it out of there. For those of you that are mechanically and electrically inclined, this is the bottom of some high voltage electrical gear in Newmark. This is a floor drain, and so we just ran into a plugged floor drain at this location. I wouldn't have wanted this to continue for very much longer. This is a mechanical room disguised as an office furniture storage depot. This was over in Newmark. The air handling unit sits back in here. Here's a piece of chilled water or hot water pipe. There are about a half a dozen mechanical rooms full of office furniture. We just asked the department to get rid of some of this stuff so we could get in there and work. This is just one of the most visually self-explanatory pictures that we have. Significant tape diffusers out there for people that are getting drafts, that are interested in controlling their own destiny. I like this one. This was catching, hopefully, a smaller amount of water from a roof leak over the building. I think this just went to a 5-gallon bucket. But it's really sad when you think about the maintenance, some of the things that are out there. This was some of the ductwork at Turner Hall. We had a significant duct cleaning project at this location. The guys worked on this for about a month to get some of this stuff cleaned up. Fume hoods. We don't think this fume hood was actively being used. We found this over at Turner Hall. If you think about Turner Hall, it was a state-of-the-art agronomy building in 1975. It's something else. It's something different today. So they don't need as many fume hoods as they had. So it's really an interesting project for them to evaluate their fume hoods. Then you get into the issue of professors giving up fume hoods and think they're giving up something and that type of thing. So it's kind of interesting. This is a thermostat over in Turner. What's wrong with this picture is this. There's oil coming out of the pneumatic lines in this building. This really didn't cause a problem with this particular thermostat, but when you get into pneumatically controlled variable air volume boxes in the building, this will take out that controller and it won't work. So it's got to be replaced. So there was a problem on the south campus area in regards to this. And it just serves, it's just a reminder that so many things need to work right for things to work properly. And this is just another hurdle. This one's recent. I don't know if you can make this out. This is duct liner insulation from Madigan. You can make it out. This is a set of turning vanes in the ductwork downstream. All this material is coming off and clogging the turning vanes, and we've got to find a solution to that. Just another interesting, highly visual picture. Let's see, where am I at? We're starting to wind down. These are some of the largest energy-saving things that we've been able to implement. Just implement more aggressive occupancy schedules. Reducing outdoor air and exhaust air quantities. Lots of maintenance work. Fixing, calibrating sensors, dampers, all the maintenance things that need to be attended to for them to work properly. We've kind of touched on some of the simultaneous heating and cooling things that are out there. We're creating a lot of temperature-controlled web pages. One of my personal opinions is we've got to bust open the black box. If we retro-commission a building, we'll catch things after the fact as time goes on, and I can catch quite a few things if I just scan through some of this material. Another interesting thing that's coming is the campus utility billing program starting in FY10. I'm guessing some of you have heard about that. I'm not prepared to speak to it, but it is something that's coming that will probably hopefully it will significantly change some culture out there. Back to you.
And then we'll just do a brief summary of what we discussed today. At retro commissioning, both teams have covered over 1 million square feet, 1,250,000. Actual savings to date is a little over $1 million. Actual energy saved is between 18 and 36% per building. The CO2 reduction for the footprint is about 5,000 metric tons, which is equivalent to 25 rail cars of coal that were getting delivered at Abbott Power Plant, which is about the emissions of 884 passenger vehicles, is what we reduced over the past year and a half. So that's all. So we thank you very much, and here's more information at our website if you'd like to note that. And otherwise, we'd like to open the floor to more questions if you have any more questions. Yes?
So in what order are you doing these buildings? Is it from the most energy-using buildings to the least?
It kind of has a bearing on how it ranks in the top 80, but also we've noticed some buildings are more inclined to invite us to their building, and others kind of don't want us there. And so that also has a determination of where we're going to go. And the little DDC control also affects how much we'll make a decision.
Have you guys looked into yet with the buildings that you've already retro commissioned and that you've got the control systems pretty well working and trending? Have you looked into any of the automated fault detection type trend analysis things where you can actually, instead of having to send an engineer in every year to look through trends and stuff, that you can use? They call them smart alarms. I have a problem with that concept, but
right.
For lack of a better way, or anomalies, where you can actually use a computer to start detecting and flagging
and
long-going system. Not so much alarm. I mean, alarms need to stay kind of at real time, but this is kind of the longer term that looks over a season and says, this is happening or that's happening. Have you guys looked into that, or are you interested in any of that stuff?
We have seen that come through, as a matter of fact, recently, within the last month or so. Myself personally, to examining that and using that technology. Carl would be able to speak more about how much we have thought about it.
Yeah, I think 3 or 4 companies have been identified to us. We're kind of talking with one of them to maybe do some demo work. We're on the very beginning of that learning curve. I haven't seen a lot of that myself, so kind of in a living and learning type of scenario with that.
Is that using the
Use
meter
that by
data? Is that using the utility data?
We're using the DEC data down. So it's not a big. The one I'm thinking of is not a top-down. It uses all the granular temperature, pressure, right down at the IO and set point level, and looking at control loops and determining when things are getting out of calibration, when things are starting to go south, and letting the computer kind of, as the problem grows, at some point it gets flagged and says, hey, there's this issue, you should check it out, and they can usually document what sometimes you can document savings, sometimes not. But I can talk to you offline about.
We looked at a couple of those, and we actually had some proposals for some of the newer buildings. Of course, you have to have all the electronic controls already in the buildings. Most of the retro commissioning activities are on the older buildings that don't have that. The other thing is that you've got to create a gateway to interface between whoever's coming in. Typically, it's on a different platform. So there's the training that Carl was showing on that we can put directly in DDC and have somebody just review it. I mean, that comes with what we do already.
Right, that's an annual thing.
Additional expense of the consultant and the integrator for a gateway in the different platform and the fees that's associated with somebody else coming and do it.
Just in the interest of disclosure, that's something that I've developed, my company's developed, and we're actually based out of Champaign. Probably one of the most installed system that's available right now, I think. I don't think there's anybody that's got too much more.
Well, we're always open to looking at.
Yeah, but I'll talk to you after that.
Yeah.
A couple years back, went to a AIA seminar with then head of FNS, Cliff Carey, and he talked about deferred maintenance. And maybe this is too big programmatic, but you guys are over here fighting the worst cases, doing the worst first. Deferred maintenance, he quoted some huge number. I mean, you bump into that all the time. What's kind of the big picture of that versus you guys have to, can you comment on that? Or
what's the big picture? Need money.
That's 4 or 5 years ago. That's kind of.
But aren't you generating money?
That's a good point. I mean, and that's one of the things that we've put requests in, to reinvest some of these energy savings back into doing more of this work. And the number, $600 million backlog of deferred maintenance fee. The fee that's funding this group, the AFMFA fee, is the deferred maintenance fee that is assessed against the students. And that is what's funding this activity.
The new building system to address that.
The new buildings is
the building system.
That's a evolving conversation at this point. It's an evolving discussion. I'm interested to see how that all shakes out. Work in progress.
Good. Did you guys consider any energy savings performance contracting, maybe inviting private investors to do that? Or?
That is another active area. Terry Ruprecht is working with that. That's also another conversation within the university.
Is there anything that can be done if the buildings are full of window air conditioners and radiators? What is the percentage of buildings on campus?
I don't know that I can give you. They're out there. I don't know that I can give you a straight answer on that. They're just on the list. Obviously, things can be done more efficiently. It takes money to do that, and capital is limited in the present economic environment. It takes money to make money on some level. So, I don't know that answers your question, but it's an item that's out there.
Could I follow that in just the same vein, office and building, single windows and old wooden frames that don't even fit well? It just seems like such an obvious low-hanging fruit to find approval. Of course, we need capital money to deal with it. Do you have a sense of the payback of just elementary switching from really leaky old windows to reasonably modern windows?
About 20 years, 15, 20 years.
Lost.
It's a long.
Well, and it depends greatly on what type of system, what type of space is it. If it's a lab building and you're changing the air, 10 air changes per hour anyway, it's not that significant. But if it's an office building, then it does come into play a lot more. But that all the newer facilities we're looking at better envelopes to begin with. Capital costs are big. They're big. Well, and the old buildings you get in to battles with historic preservation, and we're going through that with Lincoln Hall now. Lincoln Hall is going to go through a major renovation, and that's one of the items that's been discussed with IHPA for the last 2 years.
Eva?
Kind of a follow-up question to that, talking about reinvestment of energy savings funds and return on investment for various types of improvements. Have you guys worked out any kind of a return on investment number for sort of your across-the-board efforts so far?
Yeah, we're in about the 2-year payback area. We saved $1 million. We had to spend about $1.6 million in that time frame. So that gives you a feel for the numbers. Of course, we already did this thing to save that first $1 million, so it'll be a lot easier to make the second $1 million, theoretically. Yes.
Have you computed energy use intensity on any of the buildings that you're working on? Like in terms of kBTUs per square foot per year?
Those come on the top 80 list. They're already calculated for us. They tell us as we go to each building what are our current units.
And do you know about what ballpark you're working in terms of kBTU per square foot per year in these high-use buildings?
Madigan Lab, the units that I carry in my mind are about $7 per square foot per year.
Which sounds really high.
Yeah, Madigan Lab is 100% outdoor air in that building.
Some of that low-hanging fruit.
Yes. 180,000 CFM of single pass air.
Yeah, and I mean, that's a good point because, this initiative is very important. We can't afford not to do it. And that's the whole, all this, it looks to be pretty straightforward. We should be reinvesting energy savings and doing more and more of this as we go forward. And I think it's kind of catching on a little bit, but we're hopeful it'll get more widespread support for doing more of this type of work.
Well,
because it pays back. I mean, it's a year and a half to pay back. I mean, we can't afford not to do it.
The progress you're making is wonderful. I just wonder if you're getting to the point where you have a high-performance building and if you're benchmarking it against some other similar.
Well, all the new facilities that are built, part of, we do require LEED certification. Part of the process for doing that, of course, you have to meet ASHRAE 90.1 and beyond. There's an energy model for every building that's done to get LEED points. You get up to 10 credit points. think business may be looking at 8 out of the 10 credit points. So it is something we are doing, modeling, trying to get an integrated design approach to do the best we can. But that more applies to the new facilities than the old.
Are you looking to do any LEED EV, like the existing building LEED certification on any of these retrofits? Because that's obviously the first step, and if you're doing that first step, it would seem like
Damon is LEED EV certified. I haven't taken a hard look at that. I'm aware of it. We haven't approached that with any degree of seriousness to meet that criteria.
I'll say, well, we did look at doing the full LEED EV program, but the quick payback piece is the energy piece.
Yeah.
What we're doing really is just pulling, that one piece out. But what we're doing is the same process that LEED EV would go through for energy. So we've just kind of focused on that because we can get through it faster. It's more focused crew, and the payback is much.
Well, that leads to the question then. So LEED EV requires Energy Star certification for its energy side of things. Have you looked at Energy Star certification for these buildings?
It's kind of a separate program. We did sign on to Energy Star, but I think we're doing it a little bit different than that. And we do actually, we've done modeling. We've done the full building energy modeling on some of the buildings, but I'll say that it's not as cost effective to go through that whole modeling process on an existing building. The process that's kind of developed itself as we went through retro commissioning seems to be the quickest and get the best solutions, and it's really working pretty well for existing buildings.
a lot of the EV points too would require that they do a lot of stuff with systemic, probably it's hard within the university, cleaning materials, cleaning methods, and all, a lot of the indoor air quality stuff that you can't really address on a building by building basis because you got those crews coming through.
Right, but they are doing that. We're just not going through that full process building by building. They're looking at implementing cleaning initiatives that are green throughout, but we haven't tried to go through and do the certification process building by building.
But the question, I think, with the Energy Star rating, you don't need to certify, just to know as a benchmark how much your Energy Star rating has improved. You don't need to do any simulation or any other. You just instead the
based on bills.
Yeah, in the utility
yeah.
bills.
And we do that through the energy bill, and we spend $2.5 million upgrading our metering, and we're implementing that into a system. That's part of what the billing process is going to be. We're actually integrating it in its InStep product that's tied with eDNA, which is a data historian, and it's actually a billing system. But the data will be there in eDNA, and it's got trending, and it's got the permanent record for it. So we can go back and start doing the comparisons. We're doing it now on Excel spreadsheets based on the metering data we've got out of our old system. So we do that, periodically, and that's one of the things that goes in towards when we talk about our top 80 buildings. We do look at the intensity, and those are determined on where we go next. So we are looking at it. We're not just following the program quite formally, I'll say.